because I showed you this algorithm, and I think it's clear that this already improved on the naive counting of the models and searching through all the model space. But we're not done yet. We're not done yet. There are still some things that we can do to improve the algorithm, and that basically then went to become the DPLL procedure. So how can we improve what we have seen? So here are some observations. And one of them is that if we know that the literal is true, then we also know that the literal, the clause in which it is contained is true. Another observation is that if I know that a clause is true, then I can simply remove it from the list of clauses. So these are two important observations, because it basically means that if we have true literals, we can simply delete the clauses in which they occur. Another thing is that if a literal is false, then the clause L1 to L2, L3, disjunction of those, is the same as the same clause, but now without the L value, the one where I know it's false. And it's basically logically very simple to understand that if I say false or A or B can only be true if A or B, because false is always false, so it is not an option we can take. So the second observation is that if I have a clause which contains a false literal, then I can shorten this clause containing and just get rid of this false literal. And basically, the empty clause, if I can remove something, then the empty clause means false. That also helps me to get faster to my contradiction. I haven't defined this formally, but I hope you have already understood that, and you remember from earlier courses maybe, that a literal is an atom or a negated atom, and an atom is a proposition, in this case, a proposition in logic. So we start out with our propositions, and then we can negate them or not. And if we brought it down to really to the level of only the proposition or a negated proposition, then this is called a literal, either a positive one or a negative one. Yeah. Sorry, I missed the last bit. If I don't know anything, I can't do anything. It's only if I know that literal is false that I can remove the clause. We're just going to see that in a minute. This is named the algorithm that comes out of this, that I apply now my algorithm to a formula in the literal, and if the literal is contained in a clause, I can remove the clause. If the negation of the literal is contained in a clause, I can shorten the clause by just taking away this literal. And for the rest, I can check for empty clauses and return false, return true if necessary. And if I have an empty clause, I can return false. So these are now 4 improvements for the algorithm, and for the rest it's exactly the same. So I just start with an assignment, and I give a literal, and if this returns true, then I'm done, and if it returns false, then I have to try the other side. So that gives me my depth first algorithm. Let's see how this works. So we have the same set of formulae. We start out with a negative assignment to the value A. That was still the algorithm. We start with the negative assignment. So assuming that A is false, then we can basically remove all the occurrences of A as a positive literal in our clauses. Yeah? So that was this case. If the clause contains the negation of the literal, then I can shorten it. Just get rid of the constraint. Because, of course, the idea behind this is that if A is false, then it will never help making this formula true, because false or anything, I can ignore the false. So that already has improved my number of things I have to check really significantly. And I haven't checked the last one, because we know that not A is true, because that was the assumption here. A is false, so not A is true. True, or whatever you choose, is always true. So we can delete this last clause from our testing. Yeah? So that's very powerful. By just making these two rules, we now look not anymore at these full sets of clauses, but we only look at those simplified clauses and fewer clauses. And then if we assume B to be false, we can basically delete the second one, because we assume it's true. Basically, you can delete clauses if you know that they are established to be true, and literals if they are established to be false. And that's why we reduced this B here, and we reduced we got rid of this clause. But you see it all happening here. So this basically means that C has to be true and C has to be false at the same time. And actually that's impossible. So this way, this path didn't work out. Yeah? We got a contradiction by this assumption. But now we know that we can go back to B, try the same. It doesn't work because we have the same contradiction here. We go to A. Now A is supposed to be true in our algorithm. A true means that these three clauses are redundant. And it means that in this clause, not A can never be the disjunct that makes the formula true. So C has to be true. And basically, if we go through our search, we find this model, but now faster. Yeah?
How do you then know that B is false? It's not true.
It doesn't matter. It would happen if we would have taken B to be true, it would have been the same solution. But it's just the algorithm that starts always with a negative assignment. Yeah? Sorry, I was one step ahead. When we choose the C to be false, obviously it violated this last clause. So we have to choose C to be true. But it would have been the same if no matter what we've chosen for B, it would have given us both another model. It would have given us another model, but it still would have been an assignment that makes it true. Okay. So that was already a huge, huge improvement, as you can see. That helps a lot. But there's even one more assumption. And if I have, it's called the unit clause rule, if I have a clause that has only one literal, so that is this case, I have a literal and a number of clauses, then basically this literal must be true, because otherwise the whole formula can never be true. Yeah? Do you see that? Because what this basically means is, so the C will be a clause, so I have one is the L, then I have something more complicated, A or B, and so forth. But this one can only be made true because it's conjunctively read if L is interpreted to be true. For literal, so if it negates the atom itself has to be false. And this is a very powerful mechanism because it basically helps you split your search space in two, if you look at it from a search perspective. And in this case, the trick of this algorithm, and that really made a huge difference in practice, is do not do your variable evaluation in a sort of pre-defined order, but use the heuristics of starting with the ones that have these unit literals. So the literal that occurs as a clause itself. So that's the idea. Really branch immediately on unit literals. And this second one is not so important, but it's also an improvement, and that's called the pure rule, that if you have a literal only occurring positively or negatively, so only occurring with without any negation in front of it, then you can in principle, arbitrarily choose which value you want to give it. And that is also useful to start with those one and eliminate those. So let's see what happens. This is now the final algorithm. Remove the clauses containing literals, shorten the clauses containing the negation of the literal. We've seen that. That's the starting point. But then also, if your formula contains a unit literal, so a literal that occurs orphaned on its own without another disjunct, then immediately branch on this one, call the procedure on this unit or on the pure literal. And that basically made the decisive difference and really turned this into a very computational, competitive method. What happens? How does it work? Again, we start with A, we make the assumption that A is negative, so then we have these three clauses left. What does it mean, basically? If you look at this already, we have a unit clause here, and that is the clause B1 is a unit clause. The other unit clause is the C1. So you start with the first one, the B1, so B has to be false. That's immediately the next step. And you get the contradiction. And that allows us to return now on the backtrack. We can now backtrack on the B because we made the choice of the B. We know that B had to be false. So we don't have to search through this part of the tree anymore because of the unit clause rule. And we can backtrack to the A immediately. And now we have the unit clause C here, and we are immediately at the next solution. Yeah? So we found a solution for this problem, finding us a model. It's still a partial assignment, so it means we don't have yet an assignment for B, but as B is a pure literal, only occurs in the remaining ones in negative form, we can choose whatever we want for B, and this gives us a solution. So we are done with this fast algorithm. And this was sort of the most powerful heuristics that really become part of the algorithm now, that you start with a unit clause and a pure clause if in the second instance. But there could be even more heuristics to apply to. Because obviously, I mean, you've recognized that this is a depth-first search algorithm where the decision is on which is the next literal I should branch on. Yeah? And the decision here to make the branches on the unit clauses is a critical one for the algorithm, so it has become a crucial part of the algorithm. But we can even have more of these heuristics in the case that we do not have unit clauses, for example. There are various types of heuristics that have been applied, both in this particular, if you don't have any unit clauses, no pure clauses, then you still have to make a decision which one to apply next. And the idea is to have one which identifies the most constrained variables. And that is the one that is likely to create most unit clauses, because I've just said that the unit clauses really help you to reduce your search space best. And one idea for this is Mom's heuristics is most occurrences in clauses of minimum length. Basically, you look for the clauses with minimum length, and then you take the literal that occurs most often in these minimal length clauses. And so this is something that you also should look into for the exam, in practice, because it's very easy to apply. If I ask you if you give you a data knowledge base, and if you have to check satisfiability, you really have to apply this algorithm, and then you might be asked to apply a heuristic, so it's good to play around with this one a bit. And these improvements of this algorithm have really made a huge difference. So the algorithm is, as I said before, it's really old. It's now more than 50 years. In the early years, where we had very little computer power, obviously we could also calculate very little. So we were looking at 300 propositions, 600 propositions with the first proper SAT solvers, even 25, 30 years after the development of those methods. And since then, a lot has happened still, and nowadays we can really attack huge, huge problems with many, many clauses, many propositions, and so forth. And the crucial things here is, so Davis-Putnam tells us something about satisfiability. So it finds a model, or it does not find a model. It's complete. So once you've searched through all the assignments and you haven't found a solution, you can return safely. There is no solution. There is no model. And it basically is a standard search procedure as the one that we've seen last week, where the action that you take, the transition from one state to another, is the choice of variable assignment. And this search is very efficient, and basically it does that by improving over the standard truth-table enumeration by early termination. So you don't do the whole assignment, you don't go through the whole tree, but by using the partial assignments, you only have to go until you find either a solution or a contradiction. You have the pure symbol heuristics with the literals that occur in the same number of negation signs before it. And the most important one is the unit clause heuristics, that if you have a clause, then you know what the value is, and you can propagate this value down to all your clauses. So this is, in summary, is really the essence of the improvements. The early termination is, as I said, any sentence that is false, is the clause is false, and so forth. The pure one is where you have the same sign, as it's called, and the unit clause is the one where you have only one literal in a clause. And for completeness, you have the proper algorithm in the, that's the one from the book. It's the same as the one that you've seen before if you wanted to practice. So let's practice briefly. Take a look at this example, and let's take 3 minutes, piece of paper, and then let's see whether we can apply the algorithm. Okay, let's give it a go. So which is the literal that we should start with, given the non-heuristics? Volunteers, you have a 1 out of 3 chance to win. P. Can I hear anything else? Okay, let's leave it with the P. Why is the P the right answer? What are the minimal size clauses. Yeah, so leftmost two. There are two clauses of length 2, so they are the minimal length one, which is the literal that occurs, or the proposition that occurs most often in these two clauses, P, of course. So we start the procedure with P, and we can now apply on the four clauses that we have, we can apply the simplification rule. So we start with P being false, because that was how our algorithm works. So the assumption is P is false. And what happens now to our set of clauses? How can I rewrite my formula according to the rules of, I can simplify my clause, I can simplify my clause set, and then I have to choose on the next one to branch. So how do I simplify my clauses? What happens to the first clause? P is false. Yeah? So if we choose not P, then the first clause, P or not R, reduces to R because P is false. So this formula can only be true if R is false. Yeah? And the second clause, P or not Q, reduces to not Q because P is false. So then the third one is actually true because P is false, or anything else is always true if P is false. And this one is, again, is true. Yeah? So basically I now have an algorithm to apply on these two clauses. And now both of them are unit clauses, so it doesn't matter which one to start with. And basically, if I choose R to be false and Q to be false, I found a solution. Yeah? So here my heuristics was so powerful that it basically disallowed me any meaningful search. So I should choose a better example next year. But there are better examples in the practicals and in the exam, because what will basically happen if you apply your algorithm on a value where you get a contradiction, you will have to do the backtracking, and just do that by applying the algorithm as it has been written down with the right parameters and so forth. And this is sort of a too efficient way for this example. Yeah?
And with this entire algorithm, we now determine that our statement is satisfiable?
Yes, it is satisfiable if you choose P to be false, if you choose R to be false, and if you take Q to be false. And that is because this one is true, this one becomes true, this one becomes true, and this one becomes true. So yeah. Yeah? Sorry? No, I don't think so. No, I don't think so, no. So, but the search is really find the first solution. And I'm not sure how it would be to go through now in order to find all the models. But in principle, Davis-Putnam is really made for finding a model as fast as possible and not giving you all of them.
No, I thought satisfiable meant that there was at least a model that you could find.
Yes.
So it doesn't matter what you choose.
Yeah.
Right?
Yeah. Yeah, it doesn't matter. It doesn't matter. It's just an example. It's just an example for one of the models that there are,
yes,
which shows that this is satisfiable.
Yes, but it's not satisfiable only if you choose those values.
No, it might be satisfied by some other assignment. Yeah, and I wouldn't know at the top of my head which one they are and if there's one. Yeah. So basically, the worst case complexity of this algorithm goes down from O to the power of n to 1.68 to the power of n. So it remains exponential because the problem itself is NP complete, so that you have to do this in this systematic way unless you find the right solution by chance. But you might think this doesn't make such a difference. But if you look at these numbers with 50 variables, you would have to go through a search space big like this, and you can reduce it by 1, 2, 3, 4, 5, 6 orders of magnitude simply by applying a better method. And this is the kind of things that you, in automated reasoning you deal with. How can you write algorithms that even in the face of almost impossible problems, like the ones of which we know that they are dealing with NP-complete problems, and that we can't build an algorithm that is efficiently enough to deal it in all the cases, we can still reliably reduce the number of time, the amount of time and space in these examples. So these are the main properties. It shows satisfiability and unsatisfiability, of course, and you can use it for entailment. If you want to show entailment, you have to apply what we call the refutation. So you have to assume that the thing you want to see follows, entails, check whether it's entailed, and you have to edit in a negated form and show that your formula is unsatisfiable, and then you show entailment. That's very important. It's a very important thing, not very deep, but you have to know it. So if you want to prove entailment with Davis-Putnam, translate the knowledge base into closed normal form, translate the thing you want to prove the entailment for into closed normal form, add the normal forms of the two things together, and then apply with the PLL until either a model is found, and then you know that your entailment was not true, or until your search is exhausted and then you're unsatisfiable and you know that your formula is entailed. Yeah? Sorry, say it again. Because you need, sorry, the question was why is it still NP complete? So the NP completeness has to be proven differently as a property of the problem, and basically you prove it. I think it's a rather complicated proof by showing that you need an exponential Turing machine in order to do it. But we haven't found any non-exponential solution here. We have found a solution 1.6 to the power of n, which is still an exponential search space. So we have reduced the search space, but we haven't reduced it as that much that we have a polynomial algorithm. It remains exponential and thus very hard. Okay, so we're now about half of the lecture, so that's bad for my timing. Very quickly on the satisfiability modular theory, because you need it for the final assignment, for the assignment this week already, because we didn't give you a simple DPLL solver, we gave you a little bit more. We gave you an SMT prover to play with, and in principle it's exactly the same as a propositional logic solver with a little bit more input possible. And the idea is that in a propositional sense, you have a problem and a complex formula, and the question is then, do you find an assignment for those formulae such that the formula is evaluated to true? Yeah. And now, if you go to the case where you need that you might need in Schnapsen, for example, you might want to talk about the value on my hand is 16 and the value on her hand is 25. So you need somehow to compare numbers. And there is an extension of SAT-solving in propositional logic, where instead of talking about propositions, you talk about propositions that are can be evaluated to true or false with respect to a certain theory, a certain mathematical theory, for example. So whenever I have a system that can evaluate the truth of an equation, for example, then I can just put this as a black box to my SMT solver. It does the SAT solving on the basis that there is some external module that tells me that x plus 3 is bigger than 5 times 3 or something like this. And if this is evaluated to true, then I can take it as an input to my SMT solver, and it does internally, it does the same as Davis-Putnam does. but now with the input of some formula being true, evaluated to true or false. So it's a language that's slightly more expressive, but in principle it allows you to do the same propositional reasoning, but now over formulae in some logical theories, as it's called. So you could have statements such as x plus 2, z is bigger than 1, and if you know x and z, then you can input that as a formula simply like truth values or false values. You can simply consider those elements as propositions. And that is the trick in this. It's an extension in that way of propositional logic with these mathematical theories, and that is something you might need when you model your Schnapsen knowledge, and therefore we included this theorem proving. So it extends such solving by some extension, and this extension could be a software model, could be numbers or reasoning over strings and so forth. And it's a very useful and very widely used extension of those such solvers nowadays. So if you read about SMTs in your worksheet, don't be afraid. In principle, it's the same, and you can use it in exactly the same way as your SAT solvers. But you have more things. You can also talk about numbers and relations, as long as you have a tool that tells you whether one of those theory formulae is evaluated to true and false in the moment you need it. So in that sense, that's why it's included, and that's why I wanted briefly to mention it. And theories would be like the reals or the integers. You could do arithmetic over, or equality of uninterpreted functions, bit vectors, arrays, and so forth. And the only property you need is that it's decidable, and that there exists an effective procedure to check if the formula is a member of the theory or not. And of course, the more ineffective your theory is, the more ineffective is your algorithm. But in our case, for the practical purpose of the Schnapsen implementation, we shouldn't worry about it. It won't be that bad. But this is the kind of things that you can now use in your Schnapsen models. And the core types that most people that are easy to use, and I don't think you need much more. This is the propositions that we have, and then you can talk about integer types, where you can have the natural numbers. That's sufficient for modeling Schnapsen, so I wouldn't worry too much about anything else like the reals and so forth. Okay, that was quick. We still have 15 minutes, and that's incredibly short for the second paradigm of reasoning. Up to now, we have done search of models. Is there a model? Can we find a model by these searching through the partial assignments? We built our search trees like we did the first week. We searched for the model. And now we do something else. We apply some rules that we know are true based on the logical equivalences. And it's now a different paradigm. We now rewrite our knowledge into new knowledge. How does it work? An inference rule is a logical form that consists of a function which takes a premise, analyzes it, and returns some conclusions. And then basically you can, at the end of your application of those rules, you can look into the set of all the things that you have concluded, and all the things that are concluded are the things that are entailed. That's the basic idea. So the type of rules we have is, this is the most famous one, is the modus ponens one. If I know that A implies B in my propositional logic, and I know that A happens to be true, then I can derive B. Yeah? You should all have seen that. It's a sort of the classic rule, and it's a it often is written like this. So sometimes you have the two assumptions on the top and the conclusion underneath. Here you have the two assumptions with the comma separated. The meaning is always the same. If these two things are evaluated as true, then this one also has to be evaluated as true. And what you have to do if you want to prove then some properties of this, you can sorry, I'm one step ahead. These are different ways of writing down the same thing. So you could have equality, or you can say that it rewrites into, so there are sort of, that's why I say symbol overloading. It's the same idea. You have two premises, and you can add a conclusion to your system, to your knowledge base. And this, there are different types of these rules that you can apply, and the rewrite rules that I gave you on Monday, I believe, you can all apply them, because we know that when we just add this information to our knowledge base, it's logically equivalent. It's just a different way of writing the same information. So the modus ponens one is a basic inference rule in propositional logic. If I know A implies B and A, then I can conclude B. Another one is if I have A and B in my knowledge base, I can conclude A. I can also conclude B. That would be a different rule. But, and then I can write down the logical equivalences as these kind of rules, rewrite rules. So this is a list of rules, rewrite rules that you can apply. So if I have A and B, then I can rewrite B and A. And as you can see now, these are now the logical equivalences that you can reuse for rewriting. But this is sort of the powerful material you have for these two things are the same. It's the De Morgan law. So whenever I encounter this in my language, I can simply add this. And we already made use of this idea when we did the rewriting for the conjunctive normal form, of course. But you can also make use of this idea in order to find out whether a formula is entailed. Because if we have the right set of these rules, then it can be shown that everything can be rewritten that is entailed. And I will give you this in the final exam. You will get this list, so you don't have to learn it by heart. But it would still be good to practice a little bit with this rewriting, because now you can use this in order to prove your entailment, for example. So let's get back to the Wumpus word example. We have this, these facts that not P1, B1 is equivalent to P1 or P21. And the second one is B21 if and only if P1 or P2 or P3. That this was the information about the pits, you remember. And we had the fact that we had didn't have a breeze in 1.1 and we had a breeze in B2. And then the question was, can we derive whether there is a pit in 1.2 or 2.1? And basically what you do is you start out with one of your formulas in this list and you apply the rules. So in this case, it's we started out with this formula, and we have an equivalence, so we make this into into two implications. It was this rule, where is it? Biconditional and biconditional elimination. So we applied this rule and rewrote a formula like this into a formula like this. Then we do the end elimination. That was the one that I had before. If you have a conjunction in your data set, you can pick whatever conjunct and add it to your data set. Then we applied on this result, we applied the contraposition. Again, another rule here. So if I have an A implies B, I can also write not B implies not A. This is exactly what I do here. Not B implies not A. Then I can apply modus ponens because I have B11 information up here somewhere, not B at 1.1, so that's here my assumption. I can apply modus ponens. Then I apply the De Morgan rule that we had already in the closed normal form, and so forth. So this was now sort of an informed way of doing it, but if you want to write an algorithm, of course we come back to the same situation, and we have another search problem. Surprise, surprise. We have a set of actions that we can take, and that is these rules that we have. It's those three rule bases and the equivalents that we can also use. We have sort of a branching factor of, 2, 4, 6, 15 plus 3 is 18 possible actions we can take. And now the question is, how can we find the best one to guide us from our data set to the solution of our problem? So we now have not a search for models, but we have a search for a proof. Here we have the information which is very nice and useful, that we can find a solution because we have a certain property of the logic, and that's monotonicity, that all the things we can derive from a formula, from a knowledge base, remain things we can derive from this knowledge base, even if we get new information. So we will never lose information. So the good thing about this monotonicity property of the logic is that whatever we derive, we can simply add to our knowledge base. So that by applying these rules, our knowledge base gets bigger and bigger. And check it out. Try to find some solutions, some search through your rules by starting with this fact that this formula P implies Q is the same as R, implies this one, and also implies F3, or implies one of them. Just try to find out whether you can find a proof from this formula to any of those two. There are two ways of doing this. The one is what's called materialization. You take your knowledge base and you simply apply all the rules as long as you can, and you produce everything that is true with respect to this knowledge base, everything that is entailed. The other one is goal-driven. So basically, if you have a specific thing where the question, is this fact true? And then you can use the rules in the opposite order. Which rule would I have to apply in order to produce this result? It's exactly the same as we talked about last Friday or last Thursday. We have this rule-directed and the goal-directed, data-directed and a goal-directed search. And in some purposes, the one is better and the other is better. They have different properties. It depends on the complexity and so forth. But it can be far better to do this backward chaining, the goal-driven search. So these are the official terms for that. This is this forward chaining, where you go basically from your database to more information. And this one is backward chaining, where you know when you have your solution, and you try to find out how could I have gotten to this situation. I will actually talk about resolution tomorrow, because I think it doesn't make sense to squeeze this into this lecture now. So I'll take 5 minutes tomorrow with a bit of more time, because it's a very nice, very powerful algorithm. I'll talk about it tomorrow and show it. So see you tomorrow. Thank you.